Now we're here about the normal and tangential coordinates. So just a brief background about this. Basically, when a particle moves along a curved path, which is known, the equation of a motion for the particle may be written in tangential, this one, normal, and the binormal forces. So in class, I mentioned that this could be represented by F sub 4 sub z, since we're referring to the x, we're referring to the z axis basically, but by normal direction, so it's F sub b. But essentially, F sub b is technically zero. And especially if we're talking about the curvilinear coordinates of a moving car, there's no such thing as an acceleration along the z or the binormal direction, since an acceleration on the z-axis would mean disaster for that particular car. So we're primarily going to be dealing with the tangential portion and the normal portion. We're still going to be using the standard formula. Summation of forces equals to mass times acceleration. And essentially, we're going to be dealing with tangential forces, the normal forces, and of course, the binormal forces. But in this case, it's primarily zero. And they're represented as such. So to better understand this, let's take a look at a derivation problem. So what if we're being asked to determine the banking angle? So here we have the racetrack, and we're here to determine the banking angle for the racetrack so that the wheels of the racing cars shown will not have to depend on friction to prevent any car from sliding down the track. So this is primarily due to the geometry of the racetrack itself, not relying on the friction in between the tires and the racetrack itself. So we have to assume that the cars have negligible size and the mass m, and travel along the radius of curvature, which is represented by rho, at a constant speed of v. So if you're gonna draw the free body diagram of this, it's gonna look like this. We know there's gonna be a weight. This is the tangential force, and this is the binomial direction. Let's just call it z for the meantime. We have the weight equals to mass times acceleration due to gravity and the perpendicular force. And here is a theta, and this is the backing angle essentially, and this is the normal. Okay, essentially this is the backing angle. If you can look at this banking angle from the horizontal, it's how slant the road is, and should be the same one here. Okay, so the first up is we set up our equations of motion. So we start first with the horizontal, or in this case, the normal acceleration part. So the n-axis. Let's just call it n-axis. So it's going to be summation of f sub n equals to mass times acceleration n, where the normal acceleration, if you recall, is also v squared over the radius of curvature, which we can represent it as such later. The forces on the n axis, or the normal axis, that will be the nc, that'll be the normal force or the perpendicular force, and that's gonna be sine theta. So there we go. So this one here. So this is the part here. Okay, that's the nc n, and if you want to see the ncx, that will and that will be ncb. That will be here. Okay. Next up is arranging the equations, so we can set up that so that we can find our normal or perpendicular force in this manner. Let's call it perpendicular force. There we go. N, or normal force. Next up is we're gonna deal with the b-axis here, or let's just call it b or z-axis. So here is gonna be summation of fb, which is technically zero because there's no acceleration going up or downward. So our a sub b or a sub z is zero. But we have forces here. So that's we have the n cosine theta, and at the same time, the opposite one, which is weight. So we can represent it as such. There we go. So that'll be n cosine theta minus weight, which is m times g. And here we can solve for nc, and still we have unknowns para dito. So we simply isolate the perpendicular force into such. That'll be equation 2. Now we substitute we use equations 1 and equations 2 so that we can cancel out mass and isolate theta. And it will be represented as such. And mass will be canceled out. Sine theta will be going over the other side. That will be tangent theta. And that will be v squared over rho and acceleration due to gravity. And further simplifying the equation, we can get theta equals the backing angle, essentially is tangent inverse of v squared. Essentially, the backing angle is just simply the tangent inverse of the quotient of velocity squared over acceleration due to gravity times rho. Now, that's the case when we're not going to be dependent on friction, but what if we are dependent on friction? Like, okay, let's have another sample problem. Okay, so here we have a 3 kilogram disc. So this one's the disc. All right, may not be practical, but you'll be seeing a lot of examples of this in the future, specifically in your fluid mechanics. But for now, let's put out this disc. Okay, this is a 3 kilogram disc, D, represented by letter D, and it's attached to the cord. End of the cord as shown. There we go. And the other end of the cord is attached to a ball and socket joint. Okay, so we have a ball and socket joint here, located in the center of the platform. If the platform rotates rapidly and the disc is placed on it and released from rest as shown, determine the time it takes for the determine the time it takes for the disc to reach the speed great enough to break the cord. Okay, so it's the maximum speed to which to break the cord. Now, the maximum tension the cord can sustain is 100 newtons. And the coefficient of kinetic friction between the disc and the platform is about 0.1. There we go. So let's try to solve it. Now that we know our given, first things first is we need to imagine the free body diagram. So the free body diagram for a tangential and a normal part is something like this. So we have the tension here. It's going inward, okay, along parallel with the normal acceleration. And then, of course, we have the tangential force. And the parallel with the tangential force would also be your frictional force. Okay, there we go. And then, of course, we have the weight of the disc. That's about 3 kilograms times 9.8066. I think the one he used here is 9.81. That's why it's 29.43. Let me just check. Yeah. So he used 9.81 here. The book used 9.81. And then, of course, we have the perpendicular force. Let's just name it N sub D. And that is all represented here. The next one would be, we have also the radius of curvature. We already given it at 1 meter. So the first step, now that we have our free body diagram, we can now set up our equations of motion with respect to the tangential axis. I'm just going to call it axis. And then the normal axis or parallel. So, yeah, we can deal first with the forces sub n and equals to mass A sub n, just like so. And here we can determine that for n, we have the tangential. We have the tension. What else? And we have the mass. And of course, we have the normal acceleration, which is equivalent to v squared over radius of curvature, just like so. So it's going to be represented as such. We are in the positive direction. I'm going to look at it that way. And we can substitute our known values. So we have mass already, which is 3 kilograms. We have radius of curvature 1. But we don't have tension and velocity. So those are two unknowns. So we need a couple more equations here. So that'll be equation 1. Next up is on the tangential part. So we have f sub t equals to m times a sub t. So for tangential, we have the frictional forces here. Okay, and we have the acceleration as well. And then that's pretty much it. And that's going to be 0.1 times the perpendicular force. That's nd. And then, of course, we have mass here, 380. There we go. That'll be our equation 2. And then, of course, finally, we have the binormal direction, or I just call it, the z-axis in general sense, which is technically a summation of forces equals to zero because there's no acceleration on this particular axis. It's just moving on this particular tangential and normal acceleration plane. There's no moving up and down, basically, here. But for F sub B, we have the weight and the perpendicular force opposing to each other, so it's going to be represented as such, okay? All right, and then here, that will be your equation 3. Now, solving them simultaneously so that we can know the other. For equation 3, we can already solve the perpendicular force. And that's going to be 29.42, or in this case, 29. It should be 29.43 if we're going to be strict about it. And then from there, we can now solve the acceleration here for equation 2. And I believe, once we solve actually for acceleration for equation 2, we can solve its velocity technically, and now we can solve our tension. So we're gonna do it simultaneously, but I just have a quick shortcut here, and it'll be something like this. Ta-da! There we go. So the tangential acceleration here will be 0.98066 meters per second squared. Our equation from 1 here, as for equation 3, that's 29.42. Equation 2, we'll be able to get tangential acceleration. And then from equation 1, we know, actually we have a given here. We know that it can sustain 100 newtons. So that's cool. So assuming that we can sustain 100 newtons here, our Vmax, velocity mass, isolating the equation here, that will be 10 square root of 3 over 3, or about 5.7735 meters per second. Okay, so you might be asking, where did the 100 units came from? Okay, we have a caveat here. So this one is our set up our equation here. It just so happened that we have this particular phrase here, line here in our problem. The maximum tension the cord can sustain is 100 newtons, and the coefficient of kinetic friction within it is mu k equals to 0.1. So the fact that the maximum tension is 100 newtons, we can get our Vmax, or maximum velocity, since that is the requirement for this particular problem. So determine the time it takes for the disc to reach a speed great enough to break the cord. So that's one of the requirements. So velocity is needed, but we still need to find time. And the second part of this problem solving is using our kinematic equation. So now that we identified our velocity, we can now determine our maximum velocity. We can now determine that particular time just before it breaks. Okay, just before it breaks the cord. Okay, so we now have the answer, 5.7735, or just 10 square root of 3 over 3. Okay, just rewriting again equations here. So we have those values. And then for kinematics, we can simply use now the final velocity is equals to initial velocity plus the product of acceleration and time. Basically, that's it. And we need to find the time it takes for the disc to reach a speed great enough to break the cord. So the time it takes just before, Okay, so substituting the values, we have the final velocity here. And I believe it started from rest. It released from rest as shown. So meaning our initial velocity here is 0. But we already found our final velocity by using the maximum tension. And we got that as 10 square root of 3 over 3. And then, of course, our acceleration here is 9.80665 meters per second squared. And we're here to determine time t. There we go. So we already canceled out the 0 here, initial velocity. And all we have to do now is just divide both sides by 0.980665 meters per second squared. And we will have the time of 5.8873 seconds, or simply put, about 5.89 seconds. Those are the sample problems I have for the lecture. I'll be adding a few more, so just for the practice sakes, this is the reference I use. Hopefully you can do some advanced reading and do some practice problems. Thank you so much.